Hi everybody, Physics Ninja here. Today I want to do a quick video on just reviewing the magnetic force. We're going to look at a couple things. I'm going to first show you how to calculate the magnitude of the magnetic force. We'll do two quick examples. Then I'm going to show you the right-hand rule because the force is a vector and we need to know how to calculate the direction of this vector. So quick video again. If you like the video, give it a thumbs up. Consider subscribing to my channel. And if you have any questions, just leave them in the comments section. I'll get back to you as soon as I can. All right, let's get started. All right, so to get started, let's first look at our equation here. We've got the force F, and that there is going to be measured in newtons. And for the magnetic force, it's kind of different from the electric force. So we have a charge Q. Again, our charge Q is going to be measured in coulombs. So if there is no charge, there's no force. That one kind of makes sense. That's not very tricky. The next one actually involves the velocity, which is kind of odd, right? If the particle is not moving, there is no force acting on it, which is kind of strange, but there's a velocity term in there, and we'll measure that in meters per second. And the last term is the field term. In this case, if there is no magnetic field, there is no force, and our fields are going to be measured in Tesla. All right, and here's our equation. Now, this other term is a multiplication, but it's a special multiplication, and it's something we call a cross product in math. So I'm going to show you two different ways to evaluate this cross product. One of the ways is using the right-hand rule, and the second way is actually just use all the vector components. It's useful if the vectors are in kind of 3 dimensions and you're given the 3 components of the vectors. So we're first going to look at just the magnitude of the force vector, and then we'll worry about the direction of that force vector. To write out the magnitude of the force vector, it's actually pretty straightforward. Again, to write the magnitude of a vector, usually we can kind of write it like this. Since I'm going to involve magnitude of 3 different terms, I'm just going to actually just drop those parallel lines here to symbolize the magnitude of the vector, and I'm simply going to write it as F, but F just means a magnitude. All right, the magnitude of this cross product here between both of those vectors is written as something like this. The charge stays the same, that's just the scalar quantity. The next term we have is the magnitude of the velocity. The next term we have is the magnitude of the magnetic field, so how big the field is. And the last term actually, which is kind of a little bit different and shows you that it's not just an ordinary multiplication here, it also involves this angle term. Now, if you consider just this diagram here on the right-hand side, imagine I have a positive charge particle here moving in this direction over here with some velocity. So that means that this v here would simply be the length of this vector, right? How fast the particle's moving. And it's moving in a magnetic field that's at some other angle, right? It's moving in a magnetic field which is given by this vector over here. So this vector has a certain length, it has a certain magnitude, and that I can plug in over here. Now the angle theta term that comes in here, the angle theta for a cross product is the angle between both vectors. This is how we define the angle theta. Okay, so that's really important. So that's it. That's how you calculate the magnitude of a magnetic force. So now there's a couple really important special cases we're going to need to look at using this equation, and I want to highlight them in the next page. All right, so here we have 3 special cases, and I want to highlight what happens to this equation over here and how we would apply this equation to these special cases. And just something to keep in mind when you're solving problems. Number 1, I've got a velocity. I've got a negative charge here, which is this red charge, moving to the right at some velocity v, and it's moving in the same direction as the magnetic field, which is the blue arrows indicated by that vector. So in this case, you can see that the vector v and the vector b are parallel to each other. Now, if you remember how this angle theta here is defined, this would mean that for this particular case, the angle theta would be equal to 0. And as a consequence of that, if you remember some of the trigonometry, the sine of 0 equals to 0. So that would mean there is no force acting on the particle. If there's no force, it's simply going to continue in a straight line and without any deflection whatsoever, and its speed is not going to change. All right, how about this other case? In this other case, I've got the velocity v pointing to the left, and I still have my vector b pointing to the right. So in this case, actually, you have that the angle theta, that's the angle between both vectors. It equals to 180 degrees. And again, if you remember, the trig, sine of 180 degrees is also equal to 0. So in this case, there is no force acting on the particle. So it will just continue in a straight line without any deflection whatsoever. It doesn't matter how big the charge is. It doesn't matter how big the velocity is. It doesn't matter how big the field is. If the angle is 180 degrees or if the angle is 0, it's simply not going to have any forces acting on it, or magnetic force acting on it. And the last case, which is a case that often comes up, especially if you're taking some introductory physics classes, is a lot of times they place the velocity in a direction that is perpendicular to the magnetic field. Like in this case, the field is still pointing to the right, and the velocity of the charged particle, I didn't even say whether it was positive or negative, but for now, let's just consider some charged particle moving in the up direction. In this case, you could see both of these vectors are perpendicular to each other. So that means that my angle theta is 90 degrees. And I know that the sine of 90 degrees equals to 1. So the magnitude of the force, again, just how big it is, I haven't said anything about the direction yet, would be QVB. I don't have to worry about the sine theta term. That term is simply equal to 1. Okay, so just keep a lookout for some of these special cases. They do come up. Okay, so now we have to find the direction of this magnetic force term. One thing we're going to notice here is that I'm going to first focus on the direction of the vector here that's in the bracket. And I want to find out what is the direction of V cross B, and that is a cross product between two vectors. If you look, do a Google search on right-hand rule, you'll find, and look under images, you'll find a whole bunch of kind of cartoon images of right hands and all these vector orientations, and there's a lot of different ways to do this. There's even somebody who uses the left-hand rule. Do not use the left-hand rule. It's the right-hand rule. Come on now. All right, you'll often see people use this, and this works kind of good if the vectors are perpendicular to each other. However, if the angle is 170 degrees or 10 degrees, I mean, then you got to kind of, I don't know what you do with this coordinate system, but this really only is kind of useful, I find, personally, if the angles between the vectors are 90 degrees. However, the velocity and the magnetic field can be in any direction. They don't have to be at 90 degrees. So for that, I use a slight variation of this. You get the same answer as this. I'll show you something else. It's a little bit more fun. So the first thing we're going to do, step one, is you take your right hand and you place your fingers in the direction of the velocity. So there's a charged particle going this way. Take my right hand, place my fingers in the direction of the velocity. Step number two, it says curl your fingers toward the magnetic field direction. So again, if I place my fingers in the direction of the velocity, and if you imagine there's a magnetic field here pointing in this direction, I would curl my fingers toward that magnetic field. Right? I want to curl them toward the magnetic field vector. And now I go back and I check. So this is actually the direction of V cross B. And now I read the problem again and I'm going to say, well, is this a positive charge or is it a negative charge? If it's a positive charge, I'm all done. My thumb will give me the direction of the magnetic force for this problem. If I read the problem and they tell me that it's a negative charge that's moving in this direction in a magnetic field that's in that direction, at the end when I do my V cross B, if it's a negative charge, what I'm going to do is I'm simply going to flip my thumb direction. I'm going to rotate it by 180 degrees and this will be the direction of the force. Okay, so it's really three simple steps. What we have to do now is simply apply them to particular problems. So let's go ahead and do that. I got two examples where we're going to apply the right-hand rule to find the direction of the force. Okay, so here's example one. In example one, I have a charged particle, which is plus 3 coulomb, and it's traveling in this direction over here. This is the velocity of that charged particle. It's moving in a magnetic field that is directed out of the page. That's what these points signify. And I have a question. Let's find the magnetic force acting on this particle at this particular instant. Okay, so we're first going to find the magnitude. The magnitude is always kind of the easiest thing to do. And for this, all we need is QVB and multiplied by sine of the angle theta. So I know the first three terms. I'm given the magnitudes of each of those terms. So this is 3 multiplied by 600 multiplied by 0.2. And now multiplied by sine of the angle theta. If you think about it here, I have the velocity that's coming in like this. And if the magnetic field is coming out of the page, they're actually at 90 degrees with respect to each other. They are perpendicular to each other. Therefore, the magnitude of the force at the end, you just carry out this multiplication. Sine of 90 degrees gives me 1. The magnetic force, this is 1800 multiplied by 0.2. Put that in the calculator. You should get 360 newtons would be the force. And that's just the magnitude of the force. Now, to define the vector for the force, we also have to find the direction. So let's go ahead now and apply our right-hand rule to this problem. I'm going to do it on a sheet of paper, so have a look at what it looks like for this problem. All right, so this is what I have now. I've got the magnetic field here, which is coming out of the page. So out like this, the velocity is pointing in this direction. Right-hand rule says I take my fingers with my right hand and I place them in the direction of the velocity. The second part of the right-hand rule now says I curl my fingers toward the second vector. The second vector is the magnetic field that's coming out of the page. So what I have to do now is I have to curl my fingers toward the top. That's toward the magnetic field. And now I look back at which kind of charge it is. In this case, it was a positive charge. Therefore, I'm done. The direction of the magnetic force is the direction of my thumb, which is pointing in this direction. Now, therefore, I can go ahead and put that on the diagram. The magnetic force at this particular instant here would have to be in this direction. That is the direction of the force. All right, here's example 2. We have a positive charge again. It's moving into the page, right? In a magnetic field that is constant in magnitude, and the magnetic field points to the right. The velocity of that charged particle is 10 meters per second. Let's find the force again. So again, the magnitude of the force, QVB, sine of the angle theta. We could substitute everything. We have a charge of 2 coulomb. We have a velocity of 10 and a magnetic field of 0.3 and multiplied by sine of 90 degrees. Again, it's 90 degrees because the field is pointing to the right and the velocity v is into the page. Okay. Substitute everything in here. Put that in the calculator. You should get 6 newtons for the magnitude of the magnetic force. All right, so finding the direction using the right-hand rule. V is going into the page. So what I'm going to do now is I place my fingers in the direction of the velocity. Step number 2 said I curl my fingers toward the magnetic field. The magnetic field is pointing in this direction. So I have to curl my fingers in this direction like this. Right, curl my fingers toward the magnetic field. Now it was a positive charge, therefore I'm all done. Right, the direction of my thumb gives me the direction of the magnetic force for this problem. So I can go back now. The direction of the magnetic force has to be in this direction. That's the magnetic force acting on a positive charge particle moving into the page in this type of constant magnetic field. And that's the force at that particular instant. Oh, great. V cross B, positive charge, I'm all done. Gives me a force acting down. I need to highlight 2 super duper important points regarding this magnetic force. And here I got both examples here kind of shrunken down to size just to illustrate my point. Again, we used the right-hand rule to find the direction of this cross product and then looked at the charge and decided which direction the force was in. But one property about both of these cases that you're going to look at is that the magnetic force F in both of those cases is always going to be perpendicular to both the velocity vector and also the magnetic field. Okay, so that's always important. So let me write it down. It's always perpendicular to the vector v and also the vector b. Now, one thing to consider is that v and b can be in any direction, right? I could choose to throw my charged particle, right, in any direction relative to the magnetic field. However, if there is a force acting on it or a magnetic force, it's always going to be perpendicular to both of those vectors. And have a look. Right here, I've got my field coming out of the page, my velocity at this angle. Look where the force is. It's at this angle, right? It's perpendicular to the velocity vector, and it's also perpendicular to the magnetic field vector, which is coming out of the page. Have a look at example number 2 that we did. Right, I have my velocity that's going into the page. I've got my force acting down. Those 2 vectors are perpendicular to each other. Also, look at the magnetic field is pointing to the right, and the force is acting down. And what do we have? A force that is perpendicular to the magnetic field. We always have this, so double check your answer. All right, the last case I want to do is, what happens if V and B are vectors that are in three-dimensional space? You can imagine velocity going this way, magnetic field going in another direction. How would we use the right-hand rule? It works, but it wouldn't be very hard to describe the direction of the field, or of the magnetic force rather, using a right-hand rule if we have really like a three-dimensional case. So let's do one more example just to show you how to evaluate this cross product using vector components. All right, so here's the last example I want to look at for today. Again, we're going to have a three-dimensional case here. So I've got a set of axes, x, y, and z axis. And what we're going to do now is going to consider this case. So I'm going to have a charged particle. In this case, let's consider a negative charge of 1 coulomb, or negative 1 coulomb rather. It's going to have a velocity with components. The velocity vector is over here. It has a x, y, and z component given by that vector. So I can calculate the magnitude. And also it's moving in a magnetic field, and let's assume that the magnetic field is uniform in space and the direction of that magnetic field is given by this vector over here. And again, you can calculate what the magnitude of that magnetic field is. What we're going to do now is we want to figure out how we're going to evaluate this cross product here, which is again is Q V cross B. That is the definition of my magnetic force. And again, I want to figure out how do I evaluate this cross product using these vector components, right? It's a little bit hard in this case to actually do this. QVB, sine of the angle theta, to find the magnitude. You can find the magnitude of each one of these vectors, V and B. That's pretty easy to do. However, to define the angle between them is a little bit tricky, right? It's not so simple just to find the angle. At least geometrically, it'd be really, really difficult to find out what the angle is between both of those vectors. Anyway, we're going to show you how to evaluate the magnetic force using this first expression. It's pretty straightforward. Let's show you how you do that. So let's find the direction of this cross product here. I'm first going to focus on finding the direction of V cross B. And at the end, all you have to do, once you know this resulting vector, then you simply multiply it by the value of the charge, which is a scalar, and at the end you get the magnetic force. So this is really the key and kind of the hardest part to this calculation. In order to do this, again, I'm going to write this. These straight lines here signify the determinant, and I'm going to put the vector components I, j, and k. So that's a unit vector along the x direction, the y, and the z direction. Now you look at the first vector. I'm going to write it down into components. And we'll just keep it general right now, so this could work for any vector, vx, vy, vz. And also the second vector, now you just, again, write out the components like this, by, and the z component of the magnetic field. All right, so this is the determinant. And at the end, what we're going to end up doing is we're going to have an I component. We're going to have a j component. And we're also going to have a z component. Okay, the way you evaluate this, it's pretty straightforward. If I'm looking for this component, again, I cross out the row and the column where that term appears. And at the end, all you end up doing is you multiply, you cross multiply these terms over here. So the ith component looks like this. It's the Vy multiplied by the z component of the magnetic field, and then minus Vz and multiplied by By. Okay, so that is the ith component, or the x component of this result V cross B. All right, that case is pretty straightforward. Let's eliminate this one and let's find the next one. All right, now for the y component, this case is a little trickier. Again, you end up crossing out the row and the column. And this is a property of determinants when you evaluate determinants. If I'm going to still do the cross multiplication like this, I have to put a negative sign for the second component here. Okay, and then I'm just going to redo it using the exact same order that I did. So I go from the top left to the bottom right, Bz, and then minus the z component of the velocity and the x component of the magnetic field. All right, pretty straightforward. And the last part, again, let's eliminate this. I'm looking for the Z component of that V cross B term. So again, what you end up doing is you end up crossing out the row and the column where that term appears. And again, I'm going to end up doing my cross multiplication like this with these components of the two vectors. And in this case, I go back to the addition, or you always end up going from positive to negative and back to positive. And this becomes Vx, By, minus Vy, and multiplied by Bx. All right, so that's it. That is it looks rather complicated, but really that is the cross product between both of those vectors. So at the end, all you have to do now is simply multiply by Q. And let's rewrite those components. So this was VyBz minus VzBy. That was the X component of my force. Again, I'm going to use another bracket here just because, remember, the charge has to multiply all of those terms, right? All of these terms. The middle term was minus Vxbz minus Vzbx. That's in the y direction. And again, the last term, Vxby minus Vybx. And that's in the z direction, or the k-hat direction. All right, that is the direction of the force. So let's go back to our vector and simply substitute in the different components of these vectors to find our total force acting on that charged particle. So let's first evaluate the different components here. I'm just going to break it down into the different components of my force just to make it kind of easier here. So the first term here gives me my X component, so it looks like this. VyBz minus VzBy. That's it. So now you just substitute the values, right? So here you got -1. That's the charge. And all of that needs to be multiplied by this second term here. So we're going to get 10 multiplied by -0.1. So you got to be a bit careful here. Minus Vz is 6. Multiplied by By is also -0.1. Be careful when you evaluate this term. I think I got 0.4 newtons. Okay, for the second component, again, you're going to have a negative sign here. Let me just bring that to the front. So actually this one here becomes -Q, and then you get Vxbz minus Vzbx. Substitute in the components. So I get minus, and then the charge also -1, so that'll become +1. And now you substitute in the components for this one here. So you should get 5 multiplied by -0.1. Minus 6 multiplied by +0.1 in this case. Again, be careful when you evaluate this. I did it, I think I got -1.1 newtons. And the last term, again, it's just this final bracket. Don't forget the charge. So it's simply Q, Vx, By, minus Vybx. All right, check it out. Now we just simply substitute in our values. That's the magnitude of the charge, or sorry, the value of the charge, Q. The component Vx is 5, minus 0.1 for that component, and then minus 10, and multiplied by the final thing, which is Bx, which was 0.1. Okay, again, I evaluated that guy, and I got positive 1.5 newtons. So that means if I write my total force F as a vector, again, I can find the magnitude. If you know the components, you should be able to evaluate the magnitude of that vector, but this is the X component. My Y component is 1.1, and the Z component is 1.5 newtons. All right, that is the magnitude of the force, or sorry, the value of the force acting on that charged particle. If you want to check whether or not you got the right answer, what I would suggest now is that, you remember what I told you? I said that the force has to be perpendicular to the vector v, right? We have to have that. And the way you can check it is if the scalar product now, instead of the cross product, if the scalar product gives you 0, and it will, I evaluated this, so use both of those vectors and evaluate with the scalar product, you will get 0. Likewise, you can also evaluate the scalar product with the magnetic field using both of those vectors, and you're also going to be 0. Clearly, if you evaluate the scalar product between B and V, you're not going to get 0, right? This is definitely not 0. These numbers, I mean, you could check them out for yourself. You're not going to get 0 because there is some angle here between those vectors. Okay, anyway, that's it for this video. I hope you enjoyed it. Showed you how to use the right-hand rule. And at the end, really, this method works for any vector. The right-hand rule is kind of good for just simple cases. This is a little bit more rigorous and should be only used really for more complicated problems where you're given kind of 3 components and it's just too difficult to use the right-hand rule.